Welcome. Thank you for reviewing our presentation on airborne cognitive state monitoring. My name is Nick Wilson. I'm an associate professor of aviation at the University of North Dakota. I am joined by Mr. Bradley Hoffman and Ms. Jessica Van Bree, both students at the University of North Dakota. Also contributing to the study are Professor Kuyar Tavakolian, as well as Professor Thomas Petros, and graduate student Hamed Tahiri Gorgi. We would like to also provide special thanks to Ryan Krebs, Sydney Kramer, Kyle Bernhardt for their assistance on data collection, as well as EPSCoR and the John D. Odegaard School of Aerospace Sciences for funding support.
So the purpose of this study was to look at different aspects of mental workload throughout various aspects of an assigned flight pattern. We did this by incorporating 10 different students from the University of North Dakota and had them all do the same maneuvers to see what comparisons and contrasts they showed.
We have our participants from a pool of collegiate aviation students who had their commercial pilot certification. Our methods, we ended up having a baseline of physiological recordings pre-flight, and then we recorded physiological and aircraft data during standard set of flight maneuvers. We also collected the data looking at cardiovascular signals of electrocardiogram, ECG, photoplasmogram, which is PPG, and brain signals of EEG, which is electroencephalogram. Our equipment, we used the ABM B-Alert X24 to measure our EEG, and we also had ECG as well on that instrument. We had a secondary ECG on the Vitellino and a PPG sensor also on the Vitellino that went behind the ear. Our aircraft were Cessna 172S and Piper PA-28180.
We had various expert instructors from the University of North Dakota rank the different flight pattern elements that we used in their workload classifications, either ranking them as high, medium, or low, and you can see their answers represented on the graph on the slide.
The information provided by the instructors was cross-referenced with flight data provided by the Garmin G1000 avionics.
We use cognitive workload classification via the frontal theta difference between straight and level and missed approach as a comparison between the two. And we can see that all the frontal theta differences were higher based on the missed approach was a higher task load, with the frontal 3 node being the highest comparison between the two. The feature extraction step was performed using power spectral analysis, which resulted in 148 features. This high number of features is not only can increase the model training, but also by increasing the complexity of the model and negatively impact the performance and accuracy. Hence, the feature selection technique was employed to select the most important features. And we used several well-known machine models as a binary classifier to evaluate the efficiency of the selected features. And through this, we have 3 classifiers that can be determined with a high level of cognitive workload as an accuracy of 95%.
This was a really interesting study because it involved physiological data collection throughout an actual live flight sequence. Having more analyses like this in the future could really help us to improve flight safety and understand the cognitive workload metrics of pilots.